Hello and welcome to this Mr. Cole Chemistry video where I will be going through the Equilibria practice test. Okay, so question 1 wants us to discuss the temperature and pressure on the yield and rate for this reaction. Now really, it's not one question. Really, you can think of it as 2 questions, or you can think of it as 4 separate questions. So let's start with talking about the temperature. So when you're thinking about temperature, you need to be thinking about the position of equilibrium. We need to be thinking about whether the equilibrium is going to be shifted towards the right or towards the left when you increase the temperature. In order to know what happens, you have to then start by thinking about the values that they've given you in the question, which of course we are interested in the fact that the delta H is positive 210 kilojoules per mole. The key thing here, of course, is that it is positive, which means that the forward reaction is an endothermic reaction. So you have to remember Le Chatelier's principle. Whatever change you implement into the reaction, it will counteract that. So if you are increasing the temperature, which is what we're doing in this question, then the equilibrium will try to decrease the temperature. It will do that by shifting in the direction which decreases the temperature, so it will do that by shifting it in the endothermic direction, which means it's going to be shifting towards the right. Okay, so those are the things we need to have said. So the yield increases or shifts towards the right because the forward reaction is endothermic. Of course, we don't just have to talk about the position of equilibrium, we also have to talk about the effect it will have on the rate of reaction. So of course we know that the rate of reaction will increase. We know that because the amount of particles that have at least enough energy, so as much energy as the activation energy, has increased. You can frame this in terms of the frequency of successful collisions as well, but you don't have to in this context in order to get all the marks. Okay, so that's temperature. Let's have a think about pressure. So remember, in Equilibria, again, we are thinking about Le Chatelier's principle, and we have to consider what will happen when we increase the pressure. If we increase the pressure, the equilibrium will try and decrease the pressure, which means in order to do that, it will try and shift towards the side with the smallest number of gas molecules, or gas moles. In this context, that is the left-hand side, which means that when we increase the pressure, the equilibrium will shift towards the left and will therefore decrease the yield. And next thing, of course, then is to look at what it does to the rate of reaction. So it will increase the rate of reaction because the frequency of collisions has increased. Of course, some questions will expect you to explain why it's increased, where you'd be expected to talk about the fact that there are less space between the particles, or that there are more particles in the same volume. But given that this is a question that really is about equilibria, you don't have to go into that level of detail. Okay, so question 2 is looking at a Kp expression first, and then ask you to calculate the equilibrium constant for the reaction. So we'll start with our Kp expression. Kp is equal to products over reactants, and in each case, of course, it is the partial pressure of the products over the partial pressure of the reactants. Any stoichiometric values in your equation become powers, so in this case it's going to be the hydrogen, where it becomes hydrogen, the partial pressure of hydrogen to the power of 2. So there's actually quite a lot of different ways to represent partial pressure in a Kp expression. The thing that's definitely not correct is using square brackets, which is what you're used to using for Kc. The P beforehand is the typical way of showing it. The mark scheme, actually, as I'm looking at it right now, has a capital P, which is not actually the normal way of representing it. Normally we'd use a lowercase p, but it is worth noting that we tend to put the power on the P rather than after the formulae. So notice at the bottom it's P squared H2. Okay, so the next thing then is working out the Kp for the equation. So to do this, you're going to start by writing an ice table and putting in the values that you know that you have given to you in the question. So you've been given 62.8 moles of carbon monoxide, so 62.8, and 146 moles of hydrogen. 146 moles of hydrogen. The product, of course, is going to be 0. People always kind of forget to write that in, but actually it's worth putting it in, makes your life a little bit easier. And then we're told the equilibrium mixture contains 26.2 moles of methanol. So 26.2 moles of methanol. That means the methanol went up by 26.2 moles. The carbon monoxide went down by 26.2 moles, and the hydrogen went down by 26.2 times 2 moles. This means that we end up with 36.6 moles of carbon monoxide and 93.6 moles of hydrogen. Now, the next part of the answer, if you are looking at the mark scheme, does sort of combine various factors into one concept. I like to extend my ice table to give us the mole fraction and the partial pressure for each substance, and then I like to apply those to our Kp expression. Okay, so we start by working out the total number of moles, so we just add up the equilibrium moles of carbon monoxide, hydrogen, and methanol, which gives us 156.4, and then we work out the mole fraction for each of them by taking the number of moles of each substance and dividing by the total number of moles. So now that we've got the mole fraction, you work out the partial pressure for each of those by taking the mole fraction and multiplying it by the total pressure. So now we have the partial pressure for each of those substances, we can apply them to our Kp expression. Worth noting here, of course, we've got the 5.69 squared, so don't forget to square our hydrogen, because of course there's 2 of them in the ratio, and this gives us an answer of 0.0221. The mark scheme only seems to want you to have it to two significant figures, so 0.022. I don't see a good reason for that. Everything is given to 3 sig figs in the question, so I would do it to 0.0221. The last bit then is working out the units for our Kp. So when it comes to working out the units for Kp, you need to take a look at the units that we use to pressure. In my case here, I kept my pressure as megapascals, so we're going to be using megapascals to work out our units. So to start with, you write out your Kp expression, but replace each of the numbers with the unit that was used. In order to simplify this expression, we can cancel a few things out. Anyone that's a good mathematician will find this extremely straightforward, but if you're not a mathematician because you don't take maths at A level, then this might be a little bit more unfamiliar to you. First things first, we've got megapascals on the top and the bottom of the expression, so the easiest thing to do is to cancel those 2 things out. And then, of course, we need to move this up here, and when you move the power from the bottom to the top, it becomes a inverse, so it becomes minus. So Kp is measured in megapascals to the minus 2. Okay, so question 2a is both about interpreting graphs, but also looking at the Chatelier's principle. Because A is asking about whether or not the reaction is exothermic, we're interested in the effect of temperature. So we're not actually interested in what either one of these 2 lines is doing individually, we're actually wanting to compare the lines at any particular pressure. So what you're looking at then is just basically at any individual pressure, it doesn't really matter where you pick, let's say you pick here, how does the percentage yield vary depending on the 2 temperatures? Okay, so we've got a lower temperature which has a higher percentage yield, and we have a higher temperature which has a lower percentage yield. The second mark then is using Le Chatelier's principle and applying it to the statement that I've just written. So, if the yield has increased with a lower temperature, that means the equilibrium has shifted towards the right at a lower temperature. You of course can say this in the inverted way, so you can say that when the temperature increased, the percentage yield decreased, which means that the equilibrium shifted towards the left. So question B is still looking at Le Chatelier's principle, but this time we are looking at pressure. So you want to be looking at an individual line. So it doesn't matter which one you look at, you can look at the 300 Kelvin or the 600 Kelvin, but just look at a single line. So you can see that as the pressure increased, the percentage yield decreased. So this means that as the pressure increased, the position of the equilibrium shifted towards the left. And therefore there must be fewer moles of gas on the left-hand side. So if there's fewer moles of gas on the left-hand side, that means that when the reaction is taking place, you are increasing the number of moles of gas. Okay, moving on to question C. It says to explain why using a catalyst has no effect on the percentage yield. So we already know that increasing the rate is the consequence of using a catalyst. But we have to consider, when we're looking at the yield, we have to consider the forward rate of reaction and the backwards rate of reaction. If one changes but the other one doesn't, or one changes more than the other, then you get a shift in the position of equilibrium. If they don't change, there's no position equilibrium shift, or if they both change but they change by the same amount, you don't get a shift in equilibrium. And that last one is the one that matters here. So yes, a catalyst will increase the rate of reaction, but because it increases the forward rate of reaction and the backwards rate of reaction the same amount as each other, there's no shift in the position of equilibrium. Okay, so question D wants us to work out the moles of ammonia present in our equilibrium mixture. They've given us the value for Kc, they've given us the temperature, although that's probably not relevant, they've given us the volume of the container, and they've given us the moles of hydrogen and nitrogen. To help me figure out what I'm trying to do, first thing I'm going to do is write out my Kc expression. Now in this question, there is a mark for writing out the Kc expression. There won't always be, but it's always useful to do it because it helps you figure out what's going on. So the question says we have to work out the moles of ammonia. Now, of course, moles of ammonia isn't actually in the expression, but concentration is. And we can work out the moles from the concentration relatively easily. So we need to know the concentration of ammonia. So let's rearrange our expression to give us concentration of ammonia. Okay, so I've kept this as concentration of ammonia squared, and we'll square root it later. But so far, relatively straightforward. Now, of course, we've not been given the concentration of hydrogen or the concentration of nitrogen. We've been given the number of moles, but we've been given the volume as well. So those are relatively easily calculated. So let's work out what ammonia squared is equal to. And now all we have to do is square root that, and that gives us the concentration of ammonia. So we now have the concentration of ammonia. We want to know the moles of ammonia, so concentration times volume will give you the moles. And there you have it, your answer, 3.25 times 10 to the minus 3. Okay, so question 3 is an interesting one. It's asking you to calculate the Kc for the equation given to you there, but it's not giving you any values to do so. When you look closely at the equation here, given to you in this equation, you'll compare that to the original one, you can find it, and you'll notice that they are back to front from each other. So it's the same equilibrium, but framed in the opposite direction. What this means is that in your Kc expression for this version of it, the things that were the products in this one are the reactants, and things that are the reactants in the previous one are the products here. So, in framing this in terms of the Kc, things that were previously the numerator are now the denominator, and things that were previously the denominator are now the numerator. What this means is that the Kc expressions for the forwards reaction and the backwards reaction are in fact just the inverse of each other. So we know the Kc value for the other direction. It's 0.118. So this will be 1 divided by 0.118, which gives you 8.47. The same concept applies to the units, where if you look at the units in the expression above, the units were moles to the minus 2, dm to the 6, and for the backwards reaction it will be the inverse of that, so it will be moles to the power of 2, dm to the minus 6. Moles to the power of 2, dm to the minus 6. Okay, so in question 3a, we are again looking at a equilibrium that's been created. We are given various pieces of information about our equilibrium. So we're told the volume of the equilibrium, so we're told that it's 40 centimeters cubed, and we're given the concentration of A to start off with. You're told the number of moles of B and C that were added, and then you're told the equilibrium mixture, how much A is found in the equilibrium mixture. So for something like this, you're going to want to do an ice table, but before you can do an ice table, you need to work out the moles of everything initially. Two of the things, B and C, you're given the moles of, but A, you're given the concentration of. So start by working out the moles of A. Okay, so you know the concentration and the volume, multiply those together to get the number of moles of A. So you have 6.4 times 10 to the minus 3 moles of A. So now you know the initial moles of A, the initial moles of B, and the initial moles of C. And of course, because you've not had D mentioned, you know it must be 0. So you know the initial moles of all 4 substances. Let's make a nice table. Okay, so I've added in all my initial amounts. It's worth noting that I've actually kept everything to the same value in the standard form, so I've kept everything to the minus 3. The point there sort of disappeared into the 5, so let's add that back in again. So it's 28 times 10 to the minus 3, which you don't need to do at all, but actually just mentally thinking about things can make your life a little bit easier if you do it that way. Okay, so now we need to put the thing that we know at equilibrium, which it tells us the equilibrium mixture formed contained 3.9 times 10 to the minus 3 moles of A. So we know the moles of A at equilibrium. And since we know the number of moles at equilibrium, we can work out the change. So the difference between 6.4 times 10 to the minus 3 and 3.9 times 10 to the minus 3 is minus 2.5 times 10 to the minus 3. So, if A went down by 2.5 times 10 to the minus 3, B would have gone down by half that much. C will have gone up by 1.5 times that much. And D will have gone up by the same amount that B went down. And that results in B's equilibrium number of moles. Don't forget to convert your C back to proper standard form if you, like me, try to keep everything as times 10 to the minus 3. So for 5 marks, actually, that's relatively straightforward. Question B, nice and straightforward, wanting to know what Kc is. So Kc is products over reactants, and of course, not forgetting to take into account the stoichiometric ratios, so where it's 3C, that will obviously be concentration of C cubed, and whereas 2A, that'll be concentration of A squared. Like so. The question also wants you to work out what the units is. So each of these have been given in terms of moles, and we've been given the volume, so each one of these has the unit of moles per dm cubed. So if we rewrite our Kc expression using moles per dm cubed rather than each of the concentrations, and then we can simplify it down. Okay, so there's our Kc expression replacing each of the concentrations with their unit. We can cancel things out, so we'll just get rid of those two, and we then end up with this. And then when we move this up here, it becomes to the -2, which then results in this, which then, when you multiply those together, when you're multiplying powers, it becomes adding. So 3 plus -2 gives you 1, which means that your final unit is moles dm to the -3. In question C, we are going the opposite direction to normal. So rather than trying to calculate the Kc, we are given the Kc and we have to work out the concentration of one of our substances. So in this case, we're trying to work out A, and we're given the number of moles of B, C, and D. As I have stated in previous questions, our starting point is to write the Kc expression. So that's our Kc expression, but we of course are trying to work out what the concentration of A is. So we need to rearrange this to be A equals. I'm actually going to use A squared equals, and then I'll square root it later. So now that we know how to work out concentration of A, we need to work out the concentrations of C, D, and B, and put those into our expression that we've got written here. You can either just combine these together into one large equation, or you can calculate it all separately. So the mark scheme has it all put into one equation, so I'll just do it a different way to the mark scheme, and I will just calculate these all individually first. Concentration, of course, is equal to moles divided by volume. Volume is 5 times 10 to the 2 centimeters cubed, which is 500 centimeters cubed, which is 0.5 dm cubed. So moles divided by volume, so 0.21 divided by 0.5 gives you your concentration for B, and then the same equation for C and D with their respective numbers of moles. Now that we have their concentrations, we can put them into the expression that we've already used to work out the value of A squared, and then square root that to get our concentration of A. So we've plugged it into the equation. I've majorly run out of room here, so sort of shoving it on the left there, put it into the equation, and then square root it, which gives us our answer of 0.17. It does say in the question you have to use the appropriate number of significant figures. If you look in the question, they have a combination of 2 sig figs and 3 sig figs. So 0.21 is to 2 sig figs, 1.05 is to 3 sig figs, and 0.076 is to 2 sig figs. You should always use the lower value of the different values if there's a multiple different values used, because using a higher value than the minimum implies a level of precision that you don't actually have. So 2 sig figs. So the answer is 0.17. So question D is an interesting one because we see these types of question appearing, but not normally in this context. The context that you normally see this in is gas equilibria. So normally we'd be talking about changing the volume of a container of gas and therefore the impact on the pressure and what that does to the position of equilibrium. This is the equivalent to that, but for solutions. Now, in terms of understanding why the thing that happens, the easiest way of looking at this, and this isn't the way to explain it in the answer, but the easiest way to look at this is to look at the Kc expression, but look at the units in it. So if you take a look at the Kc expression here, we've got the concentrations of C, D, A, and B, but of course they're written out as the number of moles of C, D, A, and B divided by the volume. Now you can see that as you change the volume of our container, which is what we're doing when we add water in, we're increasing the volume. You can see that, well, on the top of the expression, volume appears more times. So you're actually changing the value of the top half of the expression more than you're changing the value of the bottom half of the expression. Okay, so volume appears sort of 3 times here, once here, so it appears sort of 4 times on the top, whereas it appears 3 times on the bottom. Remember, of course, each one of these concentrations is moles divided by volume, so as we increase the volume, we are decreasing our concentrations. And we're decreasing the concentrations equally, but because it appeared there is more on the top, there are more concentrations on the top of the expression than the bottom, we are decreasing the value for the top of the expression more than we're decreasing the value for the bottom half of the expression. Now, that would result in Kc going down, but we know that's not true. We know that Kc is a constant, which means that if the volume is increasing and resulting in a lower value, something must be compensating for that, and it's the number of moles. So the number of moles on the top half of the expression has to increase to compensate from the fact that the volume change is having a disproportionate effect on the top of the expression. What this results in is an increase in the number of moles of C and D and a decrease in the number of moles of A and B. What I'm describing here, of course, is a shift of equilibrium. The equilibrium is shifting towards the right. So how do we answer this in terms of the answers? Well, the first thing to note is that the concentrations all fall. So all of the concentrations fall. The equilibrium then needs to shift, and it shifts in the side with more moles, or shifts towards the sides with more moles, in order to oppose the decrease in concentration, or in order to keep Kc constant. Question 4 is a multiple choice question. It wants to know what's going to happen when various things are changed. So value of Kp on changing the temperature and the pressure, and the yield on changing the temperature and the pressure. Now the question is a bit weird, to the point where I'm wondering if a little bit of information is missing, because we've not been given the delta H value for the question. Doesn't mean we can't do the question, but does make it a little bit strange, because you can't actually tell whether some of these statements are true or false. If we can't tell whether they're true or false, then we're just going to have to discard them. So, looking at the value of Kp increase when the temperature is raised, well, we need to know whether the reaction is exothermic or endothermic. We don't, so we'll just ignore it for now. We'll come back to it if we need to consider it. Statement B, the value of Kp increases if the pressure is raised. Well, if we increase the pressure, well, what we're going to do is we're going to move the direction of the equilibrium towards the side of fewer gas moles. It does this in order to keep Kp the same. So the statement about Kp increasing is wrong. So B is definitely not right. Question C, or option C, the yield of methanol decreases if the temperature is lowered, again, relates to whether or not we have an exothermic or an endothermic reaction. We don't know which it is, so let's discard it. So far we got answer A and C, which we can't tell whether they're true, and B, which is definitely not true. So the answer should be D. Let's read it and find out. The yield of methanol decreases if the pressure is lowered. So if you lower the pressure, the equilibrium will shift towards the side with the largest number of gas molecules. The largest number of gas molecules is the left-hand side, which would decrease the yield of methanol. So yes, statement D is indeed correct. Question 5 is asking for the mole fraction of one of the substances at equilibrium. Mole fraction is equal to the number of moles of your particular substance divided by the total number of moles. So total number of moles is 0.16 plus 0.32 plus 0.18, which gives you 0.66. Now this isn't quite exactly 0.485, but it's close enough, so the answer is B. Okay, so this is a unit question. As always, write out your Kp expression and replace everything with their units. and simplify it to give you that answer there. Now note that isn't one of the answers in the question. That's not A, B, C or D. But of course, I could have converted all my units to kilopascals before I did it, which means actually I could have used kilopascals in my expression, which would result in kilopascals to the minus 2. So the answer is D. Okay, so question 7 wants you to work out what thing is going to affect the equilibrium constant for this reaction. And of course, the fact that you have to know is that Kp is only affected by temperature. So A, increasing the total pressure, nope, not going to affect it. B, increasing the concentration, not going to affect it. C, increasing the concentration, not going to affect it. The only answer that can be correct is D, because that is changing the temperature. Okay, so that brings us to the end of this video going through the Equilibria practice test. If you have any questions about any of the questions in this test, then please do leave a comment. And if you enjoyed the test or found the video useful, then please do find your equilibrium shifting in the direction of that like button.